Okay. Well, hello, everyone. Thank you very much for joining me this week for the Corundum developer meeting. I mainly just have a few status updates for today, so I'll go ahead and get into it. So as I'm sure people have probably noticed, I've pushed a bunch of driver changes up to the repository, the main Corundum repository, and I've pushed a rather complicated set of changes to my fork of the initial version of the shared interface data path. So I'm going to talk about that a little bit along with the address space reorganization that I'm planning on working on next. All right. So the shared interface data path, this is something I've talked about over the last couple of meetings. The idea is to move the data path components out of the port module and into the interface module so that you have just a single data path for all the traffic on one interface. And this simplifies things in the application section, simplifies things in the DMA engines and whatnot, because there's only one stream of data that you have to deal with. And this will support, the traffic class prioritization and whatnot. One new point that I added here is that the transmit schedulers are going to be decoupled from the ports. So any transmit scheduler will be able to send we'll be able to issue transmit requests for any port on, any priority level. And I'll get to why I made that change a little bit. Originally, I wasn't going to do that because I had one idea for how the flow control was going to be implemented, but I've since kind of done a bit of internal reevaluation and realized that my original idea was not so great. And by changing things up a little bit, we're going to be able to I think improve the flexibility quite a bit. So with this setup, you're going to be able to basically drop down as many transmit schedulers as you want. Now the default transmit scheduler is, pretty simple, and it isn't capable of sending on more than one port and isn't capable of using more than one priority level. But if we implement a more, comprehensive scheduler, a more customized scheduler, then this could be a very, very useful capability to have. So for example, maybe you want to have 2 schedulers per port running on different priority levels, or maybe most of the ports only need 1 scheduler, but you need, 1 additional scheduler across all the ports running at a higher priority level or something. This will give you the flexibility to do that, and then, configure all the schedulers how you need in software. So a lot of the abstractions for this have not quite caught up with what this architecture is going to look like going forward, but this is kind of the direction that we're going in. So the status at this point is that the initial version is working in the hardware. We can send and receive at about the same line rates if you have just a single port per interface. And the to-do at this point is the internal flow control and shared memory FIFOs, which should reduce the resource consumption, and especially on the UltraScale Plus devices will allow the transmit and receive FIFOs to be implemented in UltraRAM instead of block RAM because of the width. All right, so I showed the slide previously in terms of what the sideband signals are going to be for the shared interface data path, but the idea is on the transmit path, you'll be able to see both the source queue and you'll be able to, either see the destination in terms of the port and traffic class and potentially modify that. If we're going to support modifying that, there may need to be some consideration on the flow control side of things. I haven't gotten that totally sorted out yet. And then there's a transmit tag into user that's used for flow control and for PTP timestamping. And then in the receive direction, we got basically the same idea. We got the TID carrying the source port, the TDES carrying the destination queue. And eventually we're going to put together some logic that will allow the the application to kind of redirect where that packet is going, for application specific requirements. All right.
Alex?
Yeah.
I guess you're not sharing, or at least I'm not seeing anything.
Oh,
Maybe that's my fault, actually.
Oh, I'm sorry.
No worries.
Let me get that going. All right, there we go. Is that better?
Yeah, now we see a slide.
All right, cool. Let's see. Yeah, I'll just go back. This is a shared interface data path slide. The only difference I showed the same slide last week. The only difference is this second data point here where the TX schedulers are decoupled from the ports. All right. So, and the initial version is working on the hardware. To do, we have the internal flow control and the shared memory FIFOs. Other than that, there's not much to show. Okay. So, shared interface data path. I showed this one this last meeting as well with the sideband signals. So you haven't really missed anything if you were tuned in last time. Okay, then we have the shared interface data path flow control. So this is just a few thoughts that I have about the flow control scheme. And basically, the reason we need flow control is since you have the shared data path, if you have well, you have a difference in the bandwidth between the shared data path and the individual ports. So you run into a huge problem with head-aligned blocking, and some sort of preemptive flow control is going to be required to make sure that output queues don't fill up, because if they fill up, then that's going to back up into the core data path and block traffic for all of the ports on one interface. So the original idea that I had was to enforce this kind of at the transmit engine level, and the scheduler block could do whatever it wants. It'll just send whatever to whatever port, and the transmit engine would just exert back pressure on the input TX request path if it doesn't have, transmit credits to send something. But this only serves to move the head-aligned blocking problem unless you break this out with, a separate transmit request input per priority level per port, and you take care of all of the demuxing and FIFOing before you hand that off to the transmit engine. And this just seems like not a very scalable solution. For example, for what we're doing at UCSD, we're going to have a design which has 8 ports on one interface and 4 priority levels per port. So that gives you 32, separate transmit request inputs, and that's not great. So I did some head scratching and figured that, okay, if we kind of kick this problem over into the transmit scheduler itself and make the transmit scheduler block be responsible for, not overflowing the output queues, then one, this makes things more flexible, because now the transmit scheduler can do whatever it wants in terms of sending to multiple ports. It's not limited to, a single port. And then that also allows us to have software set up different limits on a per scheduler basis. So if you have, 2 schedulers trying to send to the same port, what you'll need to do is divvy up the transmit FIFO space between those 2 schedulers. And if one of the schedulers is not going to be using a particular port, then you could, devote all of the FIFO space for that port on that traffic class to, one scheduler or the other in software. And the nice thing is, if you get this wrong, it's only going to result in a performance penalty. You're not going to cause things to hang. So the from my point of view, this seems like probably a reasonable idea. And if we only have one priority or one traffic class and one port, then you can disable this flow control internally and ignore it, because you can just use the normal back pressure path and it'll work fine. This only becomes a problem when you have multiple ports on one interface and multiple traffic classes. And then the potential downside of that idea is that, well, now the scheduler can only use, a portion of the FIFO if you have multiple schedulers sending to the same port. So a potential extension is to add a per interface module to track transmit requests. So the schedulers, what they will do is make a request to this block first. That block will give it some, say, yes, you can go ahead and send a packet. And then the scheduler will send a packet, and then those credits would be freed once the packet is sent. And then a different scheduler could take over from that point. But this is just kind of an extension on this, because it wouldn't necessarily be, a required feature to implement this. It'll work fine if we implement a little bit of this flow control in each scheduler independently. So I'm going to put together a little module which can handle this on a, inside of an individual scheduler block. And, if you're implementing a scheduler, you can just use that, or you can implement something that's more specific to your application. So I'm not sure, Ulrich, if you guys have any thoughts about this in terms of what you guys are trying to accomplish. I do think that having the schedulers somewhat decoupled from the ports might be useful to you guys if you need to, because it sounds like you're trying to use multiple ports on one interface and then presenting these as separate interfaces to the operating system, and then doing some scheduling across those. So if we can get more mileage out of the schedulers, that and get some more flexibility there, it sounds like that could work pretty well for what you guys are doing.
Well, I guess as far as Joachim doesn't want to say something, he's much more into this topic than I am.
Okay.
But I guess we are not scheduling across multiple ports, but the first part of your statement was exactly correct. So we tend to implement one design where we present a single port as a network device, let's say, and but then there will be multiple schedulers handling on a per port basis priorities. I guess depending on the configuration, there might also be ports without any prioritization of traffic. So that's kind of coexisting. But yeah, so our target is to support a lot of like a couple of thousand different traffic classes, streams, whatever, per port, and do traffic shaping there.
Okay. I guess some of the details are probably kind of TBD, and since I'm just presenting this now, you guys probably haven't spent too much time thinking about it. So
yeah, well, we actually started doing some work on the previous implementation. So we are currently testing a shaping implementation. I guess we discussed this a couple of weeks ago, how to actually do this, and
right.
spend some time with Joachim about this. And yeah, so there is an initial implementation now available, and yeah, I guess so far that's coming along pretty good, but it's not yet ready yet. And now we have to see how to actually adapt this to this new approach in the data path. But I guess it's kind of straightforward, as it's still per port possible to schedule.
Right. Yeah. So my thought is that there's two different approaches you could take. One of them is that if a particular scheduler block is only going to be sending on one port at one priority level, you can just kind of expose that portion, basically the whole TDEST as a register in the register space. So you can just set, I want to send on this port with this scheduler. And then that's the only change you need to make. The scheduler otherwise is just doing its thing. It's only if you want to actually, really take advantage of this and have a scheduler that can send to multiple ports or multiple priority levels or whatever, then you need to do something a little bit different. And that's going to be, I think, more scheduler specific, if that makes sense.
Yes, I guess there could be a way this project could leverage this, but I think from the current definition, that's not possible to do. But I guess that there could be some extensions that actually will look into distribution of traffic across multiple ports, like I don't know, failover scenarios or something like this.
Right. Well, so I guess another thing that's useful about kind of decoupling the ports and the schedulers is that I haven't really thought of a good way to do this, but potentially you could have, different schedulers instead of like, if you have 4 ports, you could have 4 schedulers that are all the same. Well, you could instead have like 4 of the same plus like 2 of a different kind of scheduler that's, more capable or maybe less capable. I don't know. So you get a, a better resource utilization, right? Oh, Andrew, you got a comment?
Yeah, I guess I'm playing catch up. Hello, everyone. I apologise for the not being on a Corundum call questions. So when you talk about 4 schedulers, how are you affining the operation of schedulers? The schedulers are operating effectively independently of each other, and what's affine to the entry of the scheduler and the exit? So I guess I have a fairly boring mental model for schedulers, where effectively a scheduler is associated to a queue, and the most common for that ends up being a physical queue, aka a physical port. But I guess that's not what you've got in mind here.
Right. Well, so in kind of the current incarnation of Corundum, the schedulers are associated with the output ports. So each output port has its own scheduler, and the scheduler is responsible for determining which queues are going to be active on that port and making
So
all the
I
scheduling
guess
decisions as to.
Okay, if that's the question, sorry, then I might have a really stupid misunderstanding.
Let me pull up a block diagram of Corundum real quick.
Yeah, is the target board always going to have 4 physical interfaces?
No. You can
so
pick whatever number you want.
But at the moment it's 4 as a working number.
I've just kind of been using 4 for the sake of argument. I think all the current designs have one. They usually have 2 interfaces, and then on each interface they have 1 port.
Yeah, no, that's cool. Sorry, look, go. I think I probably need some background reading. Maybe I should just listen to all the other Zoom calls.
Yeah,
sorry to interrupt. I'm going to go away now.
Dig up a. I have a block diagram of Corundum around here somewhere. Just give me a second to pull it up. Oh, not that folder. Let's see. Just need to remember what paper I put, or what folder I put this in here. Let's see here. This should be under figures. There we go. Okay. Okay, so let's see if I can get this. All right, so this is kind of the working block diagram that we had for the future incarnation of Corundum. So the idea is that on the FPGA, right, we'll have 1 or more interface modules, and the original thought that I had is that each interface would show up as a network card, basically, to the operating system level. But it sounds like we're going to be kind of bending that a little bit, so you can attach multiple net devices to 1 interface module. All right. Inside of each interface module, you then have 1 or more port modules. Previously, a lot more of this internal logic was inside of each port module, but that is kind of redundant. So it makes sense to kind of pull a lot of this stuff out for a number of reasons. And at this point, each port module just has basically the transmit and receive FIFOs and the scheduler. All right, so these FIFOs then feed, the physical MACs, which go out to SFPs or SFP pluses, or 1 channel of an SFP plus or something like that. So, for example, the research that we're working on at UCSD with the circuit switching and whatnot, what we want to be able to do is treat, all 4 lanes of a QSFP as 4 separate 25 gig connections. So we can have a design which has 2 interface modules, and then each interface can have 4 ports, and each of those interfaces gets 1 of the QSFP 28s, and we get 1 lane, each of those showing up on these ports. So the changes I'm talking about now are in terms of taking this scheduler and pulling it out of the port. So the way this block diagram is drawn, the idea is this scheduler can determine which transmit queues are going to be mapped onto which port, right? Because these schedulers, they send transmit requests to the transmit pipeline here, or the transmit engine, which is responsible for, fetching the descriptors and writing the completions and reading the data. coordinating all the operations that are necessary to get those packets on the wire. At which point they'll pass through the application section and then end up in the transmit FIFO and then go out on the wire. So yeah, with the current setup, this is, I mean, it's a relatively reasonable kind of architecture in terms of how the pieces fit together. But I guess the concern is that there are potentially some scalability concerns if you want to do slightly different things with the ports. So with this setup, you get the same scheduler on all the ports. So if you have 4 ports and 4 schedulers, that works. But for example, what we're doing at UCSD, we kind of need one additional scheduler for this indirection layer that we're trying to build. So if we decouple the schedulers from the ports, what you can do is use like the first 4 schedulers to send direct data across the 4 ports, and then use the 5th one to transfer indirect data into the application section, which will then make a routing decision to send it out of one of the ports, for example.
Okay, thanks, Alex. That was you led me exactly to the answer to the question that motivated my original hands up, which is effectively what you've got is okay. In switching speak, I would say you've got 5 pipelines effectively, and then you've got this extra scheduler sits over the top and does the necessary scheduling into the application domain on the card, that is the application card presence, and then back into the interface pipelines. Okay, that
Right.
makes really good sense. Okay, one of the things is that how do you plan to couple the queuing opportunities that you have across the DMA with the queuing for each of these interface pipelines? Because of course, if you merge them all back into a single pathway, through what you've described here as AXI-bar or the PCIe HIP, actually not AXI-bar, sorry, no, just the PCIe HIP. Is there significant traffic between the 2 yellow apps, or is there just, you're going to assume, negligible?
Well, I mean, so the yellow app blocks are just where you can potentially implement application specific functionality. So you can run on the host, software, or we also have a block on the FPGA.
So the model, and this might go to Ulrich as well, is what is the mental model for the data flow between these pieces of app, or between the host-based app and the card? Look, I'm not making trouble, I promise. I'm just wondering if you end up with some sort of effectively a low entry bar switching system, so that you can end up with your PCIe presentations having multiple queues. I appreciate that. That's nice, Andrew, in the future. It's another item for the to-do list. So that you don't lose your queuing precedence when you get arrivals into the NIC, or indeed when you've got the application doing launch control.
Okay, so you're talking about the requests to the DMA engine and how those get merged together between the various components.
So I guess it's how the host to FPGA, aka the PCIe interfaces, how you're handling the multiplexing across that interface, such that you don't lose any prioritization you want to force on the host side and transfer into the FPGA, or force on the FPGA side and bring onto the host.
Right.
Traditionally, we do that with multiple queues. And unfortunately, of course, we know PCIe can make a bit of a mess of timing, but
yeah, that's true.
But by having, hey, I've been in this game a long time. I know it shits on everything. But the point is that it's not designed for certain things. It's designed for things that we don't really want to do, unfortunately. We see previous discussion about the Xilinx.
Right.
Past DMAs. And so what's the game plan here? How do you maintain priority of transactions, for example?
So right now we actually have 2 request paths going to the DMA engine. It's split into control and data. So the control path is used for descriptors and completions, and the data path is used for, packet data. I'm not making a breakdown any finer than that right now, although potentially we could consider doing something along those lines. And this allows you to make sure that you're always getting the descriptor operations completing when the transmit engines, need those. Otherwise, if you have to read a descriptor for a new packet that you want to send, but the DMA engine is all jammed up with other stuff, that's potentially a problem. So, and this is possibly an area for improvement, where right now that's merged before it's handed off to the DMA interface module. But I've been thinking about, okay, maybe it makes sense to kind of push that into the DMA interface module and reserve, some number of tags for control traffic. Now, if we're talking about prioritizing different data, different flows of packets, I haven't really looked into what it would take to do that. I suppose we could potentially add, another traffic class or two. So you could have a, mark something as a higher priority and something else as a lower priority, and get, kind of an intermediate level. So the control stuff would be at the highest level, and then maybe you could have a couple priority levels for data. That's something I haven't spent too much time thinking about, but potentially it makes sense to circle back to that and kind of think if there's a more general solution that we could drop in. That's a good thought, though, because I think right now basically all the merging is done, with round robin, except for the separation between the data and the control traffic, and then none of that has any visibility in terms of what the scheduler is doing. Right, the scheduler just issues a transmit request on some port, and then the transmit engine takes care of that, and the priority level, destination port, and whatnot, that information is not passed in any way to the DMA subsystem, but potentially it should be. So, or there should be some remapping or something that takes place there. So that's a good thought. I'll ruminate on that at some point in the near future and see if there's potentially some simple stuff that could be done to help with prioritization. Ulrich, you have something to say?
Well, our thought was, what in the end we decided against approaching this actually, but our thought was that we would have used the app space to kind of enforce at least order of packets, that the completion will actually reach the ports in the same order they have been requested by the scheduler. That was something we thought we could do in the application space then. So this yellow block there.
The transmit engine enforces ordering already.
It really enforces ordering with respect to TX requests.
Right. Yeah. Otherwise, things like TCP wouldn't work very well.
If I might ask an obvious question, who is filling in the ordering data that the transmit component is actually using? So the TX request, who is filling that in? Because if I understand Ulrich correctly, he needs that information to come down from the host app. Have I understood that correctly?
Right. So it's maintaining the ordering in terms of what order the scheduler made the requests in, and it also maintains the order within each hardware queue. So as long as you're putting the packets in the same queue, the ordering will not change between DMAing it out of host memory and putting it on the wire. Now, if you send them on different ports, that's a different story. If you send them on the same port, then the ordering should be maintained.
Okay, yeah, that makes sense. The only thing that then is missing, that you don't know how much data will end up in your pipe, right? So you're requesting the next whatever comes there,
right?
And you just know what will be there when it's there. So if you want to do something like a fine-grained TDMA or something, then you have to kind of pre-buffer and refetch data if you're not able to fill the spot. So
Not wishing to
kind
be a
of-
complete troublemaker. I was wondering if you can you virtualize the hardware queue presentation in the host, because there are transport protocols that actually need to make use of leapfrogging. And if you're enforcing the hardware queue, and I'm not sure how that's presenting in the host, I assume it's in some, it'll have to be in some protected space, but I don't know how much operating system interference you're predicting. Then you still need to be able to get your fingers into the pie and re-queue before they start heading down on their way through. Now, I know Corundum's optimized to make that path extremely short and fast, but can you understand where for example, if I'm implementing NDP, the simplest one is if I want to implement a old style source quotes XOF or something like that, and I actually want it to be hugely prioritized over everything else. How might I? Can I do that?
I mean, you would have to use different hardware queues for the different priority levels. So it's like I would need to refresh my memory with NDP, but so for NDP, do you need to send different if you need to send multiple priority levels, you would just use, multiple queues, and then you just make the scheduler aware of which queues are associated with which priority level, if that makes sense. And then, as soon as you stick something in that queue, the scheduler will put it on the wire.
Mm-hmm.
Does that answer your question?
NDP isn't the first one that comes to mind. It's
okay.
Because that's actually, that ends up having a little bit more switch specific logic in it anyway.
Right.
And I'm assuming that the app logic in this diagram that's on the card has the ability to not just enact on a single packet, but also to create and destroy packets.
Right. Yeah. Yeah. Ostensibly, we would be able to do that from the application as well. Yeah. I mean, so the application block that we have on there, it has nothing in it right now. But the idea is you can swap that out with, whatever customized functionality that you need for what you're working on. So yeah, but from that point of view, you will be able to generate packets or also drop or reroute packets. And that does complicate the flow control a little bit. And there are some considerations associated with that I have yet to totally figure out. But to some extent, there isn't a whole lot that can be done about that. So it's going to be on the application logic to either deal with transmit queues filling up or to avoid that.
Maybe to complete the view, that the app also has from a software perspective, fully distinct path to it. So there is a separate bar that you could use to access the app. So you don't even have to go through the network driver here in this case. So that could be used to, I don't know, inject data, for example, remove from the NIC data path here.
Right. Yeah. I mean, with its own bar, it has its own, portion of address space, but right now that bar just is converted to AXI Lite and then passed through to the app. So if you want to send and receive data, that's not particularly high performance, although we could certainly revisit that if we want to do some sort of a fast pass thing where the CPU can write a packet into one of the PCIe bars, and then the hardware can take over from there. That's not something that we need for the circuit switching research, because we need the scheduler to be in control of everything. So if we have packets randomly showing up on the card that the host has sent, then that ends up being a problem. But I can definitely see how that could be useful for various applications. We're not the only ones using this, obviously. So trying to figure out how some of this might work from an architectural perspective, I think would make a lot of sense.
Well, in the optical packet switching mode, how are you differentiating the control plane entirely from this system, so it's only moving data?
Yeah. So for the experiments that we have planned, the optical switches are just kind of doing their own thing, and we're synchronized with the switches with PTP. So we know what configuration they're in at any given time, but we're not, exchanging data telling the switches what to do.
Right, yeah, okay. Because the obvious contender in all of that is control plane messages are typically the ones that need to be moving, dare I say it, above the hoi polloi.
Right.
Okay, sorry, thank you.
Sure. Okay, was there anything else to discuss about the Corundum in general, or should we go back to the slides here? I just have a couple more slides. No? Okay. I'll put this away for now. We can pull it up again later if we need it. Okay, so where were we? Right, so talking about the flow control. Oops. I accidentally scrolled here. Okay, flow control. Okay, so this is something I've been putting some thought into in terms of the direction we're going with this, in terms of decoupling the schedulers from the ports, so you can kind of, mix and match for your application requirements. Okay. But the other component to this is the actual feedback for the flow control. So currently the way it's set up is the transmit engine reports back to the transmit scheduler, one piece of status associated with every packet that's sent. And this is probably not the ideal way to do this. So this is going to require some thought to figure out what's going to be the most effective solution going forward. I know the folks at MLE have some ideas on this, and they've made a couple of changes to their copy. I'm thinking it might make sense to kind of go back to the drawing board a little bit further and take a look at a couple of the other involved modules and see if perhaps there's a more general solution that's going to be, more useful. Now, this is a slide that I just put together over the last couple of days because it's going to require some thought, I think, to get this sorted out completely. But anyway, the gist of it is that the scheduler block has to be able to track each transmit operation, and it has to do this from a couple of different standpoints. One of them is the flow control, right? We need to track transmit packets as they pass through the data path so that we can ensure that the transmit FIFOs don't overflow. And that it also needs to track transmit operations from the scheduler perspective so that you can, reschedule a queue appropriately depending on whether the hardware queue is empty or not, or, depending on the packet size of the packet that you've just decided to send. Because when you make the transmit request from the scheduler, you have no idea how big a packet is, and you have no idea even if that queue has any packets in it. So the scheduler needs to get this information fed back as quickly as possible so that it can, keep its internal state consistent with what's going on in the queues. All right, so basically the three main pieces of information are the operation status. Did the operation, is it moving ahead, or did it abort because of an empty queue or disabled queue or whatever? Other aspect is the packet size. The packet size is only known after the descriptor has been fetched and parsed. So that's going to take, you're going to get that information at a slightly different time after, after the first piece of the DQ has taken place, and it's been determined whether this transmit request is actually going to send a packet or if it aborts. And then finally, once the packet actually, is handed off to the MAC, then the output FIFO space is freed, and that should be tracked. So you need a final kind of transmit completion notification saying that, hey, that packet's been sent, and you can free those transmit credits and, send more data. And the other thing is that these pieces of information are coming from different points in the transmit path. So there's a question of, what is generating data and when, and how many interfaces do we need to transfer this effectively? And, if we have, one interface or two interfaces or three interfaces, what data are we going to move over what interface? And then also, what is consuming that information? So I think from the flow control perspective, you basically need all three pieces of information, right? Because if the operation aborts, you free all the flow control credits. Once you know the packet size, then, I mean, you have to assume that whenever the scheduler sends a packet, that it's going to be an MTU frame, because you won't know until you actually read the descriptor. But once you've read the descriptor, then you can free, the difference. So if you want to send a, 15, if you want to send a packet, you reserve, 1500 bytes or whatever the configured MTU is of transmit credit. Once you've read the packet, you realize, oh, this is actually only a 64 byte packet, then you can free 1500 minus 64 bytes of transmit credit and use that to, issue more transmit requests. And then obviously you need to free the transmit credits once the packet has actually been sent. So all three pieces of information are really needed by the flow control components. But for the scheduler, it mainly just needs, the first two, right? It's got to know if the queue is empty, and it's got to know the packet size once it's actually sent. So right now, we just have one interface that kind of reports all of this to some extent. But the problem is the timing, because either you get that, you get the transmit status back once the status has been fully determined. So either you get it back immediately once the operation has failed, or you get it back once the packet has actually hit the wire, which is fine from a flow control perspective, but it's a problem from the scheduler perspective, because you'd like to know that packet size, once the descriptor has been processed. So I think what the MLE guys have been doing is adding another interface to report back the size once the descriptor has been parsed. But I'm almost thinking it makes sense to split this into three interfaces. One of them that will indicate whether the operation has aborted early, due to the queue being empty. A second one to indicate the actual packet size, and then a third one to indicate once the the operation is completed and the packet has been sent. So I guess what I need to figure out at this point is kind of the semantics for these. So for every packet that we send, are we going to get a response on all three interfaces, or are we only going to get a response on some of the interfaces? So for example, if a packet transmit operation is aborted, then I guess you wouldn't get a response potentially on the other two interfaces indicating the size of the packet and the transmit completion. I don't think this is going to be I don't think that sort of an implementation would be a problem. But I need to sit down and take a look at, how the transmit schedulers are implemented and whatnot, and see if that's sensible. I'm not sure if the folks at the MLE have any thoughts about this, splitting things up a little bit further than just peeling off the descriptor.
Yeah, I guess we kind of already have at least these three pieces of information. I mean, the abortion is communicated by simply saying, yeah, there's nothing. So I guess we have that piece of information.
Right, you have that piece of information, but it's more a question of timing, right? Does it make sense to present kind of all this on one interface, or does it make sense to split this across several? Because right now the issue is that these pieces of information are being generated by different components to some extent, and there's some merging that takes place inside of the transmit engine to because basically right now the transmit status that's returned, it's either coming from the descriptor fetch operation failing, or from the transmit complete, and that has to be merged. Now, if we present this on different interfaces, then we can remove that merging logic. That's kind of my thought for using multiple interfaces. So I'm just not sure if you guys have any thoughts on that.
Okay, no, that makes sense. Okay, I guess I didn't realize that merging as such.
Yeah, it's the design that I had for this is just, okay, you send one transmit request, you get one transmit response. Very simple, very clean. But in order to implement that, it's a little bit dirty, because you can get a transmit response at different times under, different circumstances, right? Queue full versus queue empty. You want to know immediately that it failed so the scheduler can, stop trying to send stuff on that queue. But potentially this isn't the best way to go forward. It may make sense to kind of revisit the, one for one sort of exchange, and maybe have multiple status ports that can be utilized by the transmit scheduler and by the flow control components to, potentially make things a little bit more performant, a little bit more flexible.
Okay.
All right.
I
Well,
don't know, my first thought now were that I guess there is only two different timings, isn't it? So it's the evaluation of is something there and how much is there is very, from a time perspective, quite close together. Just the other one, the third one, how much was there? That's much later, right? Isn't it? So otherwise I would say let's merge the first two and have a second queue for the completion size.
right. Well, okay. So the final completion doesn't really indicate what the packet size is, because that second operation would have informed you what the packet size is, right? Transmit complete
Yeah,
says
right.
that packet has been sent, so you can free all of the transmit credits associated with that packet.
Yeah, that's right.
And there could be a delay between knowing the queue is full or empty and knowing the packet size, because you'll know if the queue is empty before you've read the descriptor, right?
That's true. Yeah.
And then potentially maybe, so right now all the descriptors have to be DMA, which is not great, but with the variable length descriptor support, we'll have a cache of some sort for storing descriptors and whatnot, or at least, partially read stuff. So we may be able to return one relatively quickly out of the cache instead of having to go all the way to host memory and read it. So potentially there could be a delay between, knowing the queue is full or empty versus knowing the actual packet size, if that makes sense. So that's why I was thinking it may make sense to split those, because the first one is just, oh, hey, it failed, or this request is moving ahead. And then the second port is saying, okay, that this request is for a packet size, XYZ, as was read out of the descriptor. And then the third port would say, okay, this request is now finished, right? Because it's been sent. I guess it's mainly just a question of kind of semantics. So like if
Yes.
the first port says that operation failed, right? It's not going ahead. Are we still going to generate a transmit completion saying that operation is completed, right? Because that would require merging because those are coming from different components. Or are we just going to say, well, if the first one says it's failed, then you don't get a transmit completion at all because nothing was sent, which I think is fine. We just need to, make sure everybody's on the same page about how it works, and the scheduler and flow control components and whatnot are all aware of the semantics of this. I need to sit down and start working on the flow control components, and then it'll probably become pretty clear as to, whether the scheme is going to be workable or not. I think it is. I don't see any particular reason why it wouldn't be, but food for thought. And I want to try to get some of my ideas to you guys sooner rather than later, so we can all mull it over and see if it's going to be a workable idea, or if there's some major potential problem, so we should rethink it.
Totally makes sense. So thanks for introducing this here, right?
Yeah.
Cool. Yeah,
right.
But I guess you're right. So once you're looking into the details of the flow control, it probably becomes very obvious how to do this actually.
Yeah, I mean, I like to design stuff at a high level from the get-go, right? And just say, here's how we're going to do it, here's how it's going to work. But you don't always know what all the corner cases are going to be until you actually sit down and you start working on it. So that's kind of what happened with the flow control. It's like I had one idea, I sit down, I start to implement it. I'm like, yeah, okay, this is a problem. So I guess we won't know for sure until I actually put together some of the kind of the first implementation of the flow control components, and we'll see how it works. And I guess I think I'll probably need to make some modifications to the scheduler as well to handle these, separate inputs. Or actually, maybe not. I think the current round robin scheduler, it only cares whether the operation succeeded or not. So I think if the operation succeeded, it doesn't even use that information. It's just if it failed. I'll have to take a look at that. But yeah, so I think the current scheduler really only uses one of these 3 ports, but the flow control stuff needs to use all 3. Anyway, we can discuss this further, later on once people have had some time to, sink their teeth into it and mull things over. All right. Anyway, moving on.
A quick question.
Yeah, sure.
Regarding these, the scheduler and knowing if the queue is empty or not, just an idea popped into my mind. I mean, the scheduler is currently getting a doorbell as soon as something is in a queue.
Right.
Why not make it so that the scheduler also gets another doorbell which says empty? So it's rather a mechanism where the scheduler gets that information kind of pushed into it instead of,
So
requesting that information.
Right. So, I mean, part of the problem is, what do you do with that information? Because the way the scheduler works, or at least the current round robin scheduler, is when something is scheduled, it gets pushed into a FIFO. So if you get a notification saying that queue is empty, well, you can't really go remove something from the middle of the FIFO and then move stuff down. It doesn't,
Right.
the RAM doesn't really work that way. So, and other schedulers get more complicated, right? If you have like a weighted fair queuing scheduler, you schedule something by sticking it in a priority queue. And usually you can only access the top element, right? You can pop the top element off, or you can insert something which then propagates down into the queue somewhere.
Right. So it could be that another doorbell could save requests in the future. At least the scheduler then would know, well, I can't do more. I know it already, but the thing which is already in such a FIFO is, well, it has to be done. It has to be dealt with.
Right. So kind of my model for the current setup is, kind of how files work in Linux. You don't know if a file is empty or not until you've read all the way to the end and gotten end of file indication. And then you've gotten to the end of the file, but because something else could be writing stuff to the file. So with the scheduler, it's the same kind of thing. You don't know if there's, because you could have multiple schedulers pulling stuff from the same queue. So you don't know, well, one, when you get a transmit, when you get a doorbell, that could correspond to multiple packets because of the way the driver works. It could queue multiple packets and then issue a single doorbell. So it's guaranteed that when you get the doorbell that something has been enqueued, but you don't know how much. And there could be multiple other schedulers pulling stuff out of the queue. So the way I kind of designed the scheduler is to err on the side of the queue not being empty, because if the queue is empty and you make a transmit request, it's not really that big of a deal. But if the queue has some packets in it and the scheduler thinks it's empty, well, then you have a problem because those packets never get sent. So,
Right. Okay.
Yeah, I mean, potentially there are some other options. I don't think it would be too hard to add another kind of, negative doorbell, if you will, indicating that a particular queue is empty. But at the same time, I'm not really sure if that would help you very much, because I think a lot of schedulers are not going to be able to do much with that information anyway. So part of the thing with the schedulers in Corundum is that they're designed to make the best use out of the FPGA logic resources available. So that means we're using ultra RAMs on the UltraScale Plus devices to store all of the queue state information, because you get to deal with 8,000 queues or something like that. That's kind of the only option for storing that. So if you're using ultra RAM, that means you have one read port and one write port effectively. Well, I mean, you have two read write ports, but we just use one for read and one for write, and that's it. So if you get some asynchronous doorbell that comes in, there's a question of, how do you handle that exactly? Right now, we put those doorbells into a FIFO, which could potentially be a problem. If the FIFO overflows, then you might lose a couple of doorbells, which is potentially a problem. But, we'll cross that bridge a little bit later, I suppose. And then periodically when things are idle, the scheduler will pull stuff out of the doorbell queue and go, mark those queues as being active and stick them in the output FIFO. But we don't really have a good way of, changing the state on a per queue basis without, adding another back pressure path or something. So, and that internal pipeline can only process, one request per clock cycle. So if we have to share that with stuff marking queues as full and stuff marking stuff as empty, it becomes potentially a performance problem. I don't know. It's something to think about. It's an interesting idea. It would be nice if there was a more clear-cut way of, indicating that queues are empty. But well, I guess the other thing too is that you're still going to have to deal with requests failing, right? Because it's possible you're going to issue a transmit request, and then another scheduler is going to have a transmit request come back from the queue manager or whatever, and then your transmit request is going to fail because
right. The
so
problem is still there.
Yeah.
It might be a smaller problem, but still there, basically. And all the other stuff which you just mentioned.
Right. Yeah. I mean, kind of my thought is to maybe instead of trying to find a way of informing the queue manager that a queue is empty, is just to try to reduce any costs associated with a failed transmit request. Right. So right now, the only problem with those transmit requests is they eat up a space in the transmit engine's, tracking table, basically. And I need to find a way to fix that without introducing reordering so that those entries can be freed once once those operations have failed, so they can be reused before the whole table cycles through, because that means you'll kind of get stuck behind a if that whole table gets filled up with failed transmit requests, then you can't send any packets until that first packet actually gets sent, and then all those entries will be cleared, and then it can go again. So that's mainly the problem that you run into right now with the current setup. I don't know how big of an issue that is from a performance perspective, but we'll see. I think it is a question of, during normal operation, how many queues are you using? How often are they full, right? If the queues are always full, then it's not a problem, right? Because you're not going to have any operations that fail. But if you're having queues continuously switching between empty and full, then, you could potentially run into some problems here. A lot of this stuff is things that I'm hoping to connect up to the statistics collection subsystem, right? So you'll be able to, once things are a little bit more polished, you'll be able to look into the statistics counters and see, okay, here's how many, descriptor requests were issued. Here's how many transmit requests were issued. Here's how many transmit requests failed due to queue empty or whatever. So I think that will all be super useful for performance tuning once I kind of have newer versions of these modules put together and integrate some of this stuff. Anyway, good stuff to think about though. And, if you guys have any ideas, feel free to ping me on Slack or whatever, and we can discuss.
Okay.
All right. Well, let's see. Moving ahead here, I have a couple of additional slides on stuff that I've been working on. Driver cleanup. Over the last few days, I've been making a bunch of small changes to the driver. So I removed a bunch of unnecessary parameters. There was a whole bunch of stuff that was getting netdev priv arguments passed to it instead of just pulling those out of a data structure. So I shuffled some things around. I rewrote the interrupt handler to use the atomic notifier chain. So in this case, every time you set up an EQ, it'll automatically, or when you activate the EQ, it'll connect with the atomic notifier chain instead of the kind of screwy, loop thing where every time there's an interrupt, it loops over all the event queues to see which ones are associated. Yeah, okay, that's all been rewritten. I don't know if it makes much difference to performance because of how the nappy polling works, but it's a little bit cleaner now. I also changed a bunch of stuff to pass structures instead of indices. So if you're associating, transmit queues and completion queues and event queues, then instead of passing the index of the queue that you want, you pass just the actual structure. And part of this is for, when we have multiple net devices attached, those net devices are only going to have, a subset of the queues associated with each device. So, if it's an index, are we using, the zero-based index of, the little array that you have in the net device, or what? So by passing structures, it eliminates any kind of ambiguity there. I guess another thing maybe that I should do is add some assertions to make sure you're not passing structures from, other interfaces, because that's not going to work. But yeah, the idea is that once you pass the structure, then, internally it will figure out what index that's associated with, and it'll do the right thing in terms of setting everything up. The other thing I did is I split the buffer allocation from the ring creation. So this means that you can change the ring size without having to destroy and recreate the entire ring. And then finally, I split the interface from the net device. So right now it's still only 1-to-1, but the idea will be to kind of improve this connection a little bit so you can attach multiple net devices to one interface, and then you can divvy up the queues however you want, basically, on those net devices. And the idea is that the interface will be responsible for creating all of the rings in the first place, and allocating just a little structure to keep track of the state. And then the net devices will be responsible for allocating the backing buffer for the actual ring buffers. So in that case, if you're not using a queue, then it won't have a buffer allocated for it. That's about it. I don't know if I also backported all these changes, and they're all pushed to the main Corundum repository. Oh, I guess another thing that I did as well is with the rewrite of the interrupts, I peeled that off into a separate file just for interrupts. So hopefully that'll be a little bit easier for the ARM integration, because we can just add the setup and tear down calls in there for the platform device, in addition to the PCIe ones. I'm not sure if folks at MLE have any thoughts about that. I just pushed all these changes over the last couple of days. I'm not sure if you guys have had a chance to take a look at the actual code.
Yeah, no, sounds good. No, I didn't have any time up until now to look at it.
Okay.
We will do though.
I mean, unfortunately, it does mean probably a little bit of work for you guys to report some of your changes and adjustments over to this, but hopefully this is going to be more flexible going forward, especially having the net device and interface split, where you have multiple, where you're going to expose the individual ports as separate interfaces at the operating system level. So anyway, figured I would get that out of the way sooner rather than later, so that you guys can start hammering on it. So yeah, right now, I mentioned before, it's basically just a 1-to-1. The interface creates a single net device, and the net device just grabs all the queues from the interface. We need a better method for doing that. I'm not sure what it is. I'll do some thinking on it. If you guys have some ideas, I would be happy to make whatever adjustments are required. But at least we have the separation now, so so we can start working with that. All right. And then, so that's stuff that I've done. The next thing is the register space reorganization. And this is something that I'm going to start working on, because we can, start versioning internal interfaces with this. And as I implement, variable length descriptor support and the let's see, the kind of reorganization of the schedulers, then we'll be able to take advantage of this. Anyway, so the idea, so MLE guys gave me this idea, is to use kind of PCI Express config space style blocks for functionality inside of the design. And each of these blocks will have a header that specifies basically, block type, a version, and a next header. And the idea behind this is that the offsets to these blocks are not important. You can move things around as necessary. You just need to make sure that all of the pointers are correct. And this makes things easy to enumerate, because the driver doesn't it doesn't need to look at, specific addresses and, have some preordained, understanding of what these addresses mean. It just enumerates over these blocks, and then you could have a list of what all the block types correspond to. And then, software can ignore blocks that it doesn't recognize, so you can add some debug code or whatever that you can poke at from a user space application, and the driver code will ignore it basically. Or you can implement it later or whatever. And the blocks can either contain registers directly, or they can contain pointers to separate sets of registers. So I don't think it makes sense to attach these blocks to, large sections of registers, because this just becomes wasteful of the address space if those large blocks need to be aligned. Attaching headers onto things is kind of antithetical in terms of alignment when the payloads are a nice power of 2 in size. So this is, if you've worked with PCI Express at all in terms of TLPs, you'll know what I mean there. They pack nicely if you don't have headers, but as soon as you add the headers, things get all screwed up. So so for example, for the interfaces, we'll have like a block describing each interface, and then we'll have an offset to the start of that interface, instead of having the block and then the interface following the block. Or for the schedulers, for example, same kind of thing. We'll have a block describing the scheduler and some registers for controlling the scheduler, and then we probably have to have a way to control the individual queue states. So we'll have a pointer indicating where that section is. So I think that'll be a nice compromise in terms of being able to support the various components of Corundum. And additionally, the blocks give you the ability to do kind of fine-grained versioning. So you can version the individual components, and as you make modifications, you can bump version numbers. This means breaking changes are less of a problem in terms of that the driver will refuse to bind to something or complain bitterly if the version number is incorrect, versus attempting to talk to something and getting everything all screwed up because it's using an older version of the layout. So we can potentially support multiple versions or variants of the same component. So if you have multiple types of schedulers, these can expose different type fields, and then this can be sorted out in the driver. We can have different code for each type of scheduler, or in the user space application, same kind of thing. And this makes it really easy to add and customize components, right? Like I said, because the software can just ignore things that it doesn't recognize. And the status of this right now, I'm kind of determining the block formats for some of these pieces. And there's definitely a concern of, do we have a lot of little blocks, or do we have a smaller number of larger blocks? So it's like for the FPGA ID, do we want to roll that into a design ID block, or, does it make sense to keep that separate, or do we roll that into the firmware update block? Not sure. So I got some head scratching to do. But what I'm thinking for the header is to do, I think I'm just going to do kind of what was described in the document that, or not the document, but in the screenshots that Ulrich sent me, in terms of, we'll have kind of 3 D words, one for a type, and we can split that into, upper 16 kind of vendor ID, lower 16, whatever you want. And then the second D word for the version. And I'm thinking we can do, 4 bytes for the version. We can do like major, minor, patch, and then extra. I don't know exactly. We'll have to figure out what makes the most sense there. But I think that makes sense. And then the third one would be just an offset to the next block. It may be possible to kind of squeeze these together and save a few bits, but I don't think the savings are going to be, worth it necessarily. The other concern I had is, okay, that's 3 D words. If you made it, 2, then it'd be a nice factor of 2. But for any one of these blocks, you're going to have at least 1 register. So, if you have 1 register or 1 offset, okay, that brings it to 4. Any more than that, you're going to be at, 5 or 6 or 7 or something. So I honestly don't think a 3D word header is going to be a major problem. And for small headers, we don't need to worry too much about alignment, because I have a my register space abstraction modules means that we can kind of piece together things with any alignment. They don't have to be naturally aligned as you would for an AXI Lite interconnect or something like that. So those are kind of my thoughts with regards to that. What I might end up doing is creating like a wiki page or something, or Google Doc with the block formats that I'm putting together, and then we can, you know, poke holes in that, and at least in terms of some of the just general design ID and whatnot, and make sure that everything looks good there. And then we'll probably also have to have a list of IDs somewhere. So anyway, that's kind of my thoughts in terms of the register space reorganization. I'm going to work on that over the next couple of weeks, and we'll see what that looks like. So once I get that sorted out, I guess the other thing I got to figure out as well is how the driver and the user space tools are going to enumerate all of this stuff and keep track of it. I don't think it'll be that big of a deal to do that, but you know, got to sit down and implement that, make sure it all works. I'm not sure if the folks at Emily have any thoughts about this, or, I mean, sounds like it's basically the same scheme as what you guys have used on at least one of your products, so should be pretty straightforward.
Yeah, sounds like it, yes.
All right. Okay, well, that's about all I got in terms of updates for stuff that I've been working on over the past couple of weeks and will be working on soon. After I get the register space reorganization done, I also need to start working on the variable length descriptors, which is definitely going to be a significant performance improvement, but you know, we'll cross that bridge when we get there. Also, I know I've had people asking about, you know, versioning stuff. I'll start versioning the overall repository once we get to what I consider to be kind of a stable release, and this is kind of the checksum, or the the checklist of stuff that I want to accomplish by that point. So the application section, that's done and integrated. The shared interface data path, working on that. Self-contained checksum offloading, that needs to be done. The idea is to remove the checksum fields from the descriptor. This will be necessary for RDMA support, where everything is self-contained to the hardware. And this is also going to be, I think, a useful block for the current design anyway, because you can use it from the application section when you're making custom packets. Variable length descriptor support for, you know, performance reasons and whatnot. The register space reorganization, I guess I should mark that as in progress, because I'm starting to work on that now. And then I also want to get the on FPGA management software operational, which will take care of some of the board level management. So once all of that is squared away, then I think we'll be in a good position to start, you know, versioning the overall design and maybe trying to put together some sort of a release schedule, something like that. Not sure, but that's the idea. Once we get closer to, you know, having all of these things operational, then we can start some discussions along those lines if it makes sense to do so. All right, so that's about all I got for today here. I'm not sure if anybody has anything that they want to discuss. Definitely had some pretty good discussions though.
I've got one thing where that's completely non-technical.
Fire away.
and there is a big European open source conference coming up in early February, the FOSDEM.
Okay.
And I thought about maybe we want to do a little joint talk there. There is an open source hardware CFP. I will just forward this.
That's a good
to
thought.
you.
Yeah. All right.
And so this year, or this time, it's again completely online. But anyway,
okay. Rick, would you mind sending that to me as well, please?
Yes. Do I have a contact of you? Then I will send it to you. Maybe I just
Google Andrew Moore Cambridge. I'm the only one.
Okay. No problem. And I actually, you're right. I just put it in the chat. Somewhere I got this open. Yeah, this is the CFP.
You got to find one of your 500 tabs on 500 windows, you know.
Exactly. I guess that's it. So that's the CFP for this Libre Open VLSI and FPGA dev room. And the first item on the desirable topics is open hardware projects. So I guess that fits pretty well into this. And in the last time, so I have been there in person 2017 and 18, I guess. And then I wanted to be there again in 2020, but yeah, well, obviously things went differently on the world. So I haven't been there. And so it's a really nice conference, pretty big actually. So it's about a couple of thousand people coming there.
Yeah.
Very crowded. Everything is recorded and archived publicly, so you can go there and access almost every talk that has been there since they started, and it's 21st year, 20 something years ago. So yeah, it's I think it's about 20 minutes. That's the regular format there. The CFP doesn't mention any constraints, but in the past, most of the tracks encouraged to stay within this boundary. Then they have an additional 5 minutes Q&A, and then you can have 5 minutes to change the room, which is never enough, but anyway.
Right. Yeah. I
So,
mean, that sounds like a good idea. Yeah. It looks like the deadline is what, the 28th, December 28th. So I guess,
yeah, I
I'm not
guess
sure what we need to
that's
put together
manageable.
exactly. Probably just a title and abstract. Okay.
Yeah, I kind of
Funny
started
titles are
with
required. Well, oh, that's supposed to be struck out. Appreciate it. I see.
Yeah, it's funny folks there. Yeah, sadly we can't do the best must-have beer event on the Friday prior to starting the conference, but yeah.
Well,
Yeah,
maybe
cool.
we
So
could maybe we could do something like that informally via Zoom or something, you know. The conference is virtual, so okay, let's have the pre-conference get together virtual as well, you know.
Yeah, I guess they actually did this last year. Yeah, so I guess it will be there, and otherwise, yeah, you're right. We can do this anyway.
Yeah.
Yeah. So maybe I would just go ahead and grab some stuff together, and then I don't know. We can.
Yeah, we can
Start from
discuss
there.
that separately, perhaps. I'll also
Exactly.
mention that to the folks here. I don't think there's really anything to add, particularly in terms of, you know, just the core design. But yeah, because it's not related to the research that we're doing. It's just Corundum. So yeah, that could make a lot of sense. I think.
Right. Yeah, it's just spreading the word, right?
Yeah, definitely, definitely.
Yeah. Okay. That's it already.
All right. Anybody else have anything they want to discuss? We're over time again by 20 minutes, but that's, in my mind, that's a good sign. That means we got plenty of stuff to talk about. So no, that's it. All right. Well, I guess we will reconvene 2 weeks from now, probably. Let's see. What is it? Are we starting to run into weird stuff? December 27th.
Yeah, I don't
It's
know.
not too close to Christmas or New Year's, but I don't know. We could skip that, maybe. I don't know. Do you guys have strong opinions one way or the other? If all the MLE guys are out, then there's no point. But if you guys are going to be able to join, then I guess we might as well.
Well, as there is not so much to do other than meet online, I don't know. So I guess I might be joining, but actually there won't happen much on our side. So next week will be already a slow week for us. So people start entering vacation.
Right.
So I guess here at MLE, I guess most people are out from at some point next week until almost like 7th, 8th, 9th of January, because there is another public holiday here on the 6th of January. A lot of people just cross this one as well. But yeah, times are different this year, as you can't do much due to the pandemic situation. Maybe people do work, not sure yet.
Okay,
yeah,
so today is the 13th. 2 weeks would be the 27th. 2 weeks after that would be the January 10th.
Yeah, then we're all back, at least here.
All right.
Yeah, it's the 10th, right?
Yeah. Okay. So I guess we can call the next one as being the 10th. Then we'll skip the next one and then meet one after. All right. It's the holidays.
Okay.
People aren't going to be doing much, so I think that that makes sense. All right, I'll include that in the follow-up email. That I send around to
Yeah,
everybody.
makes sense. Otherwise, the others show up and just wonder why nobody's there.
Yeah. Well, I mean, we have a
Okay,
mailing
cool.
list, so I would hope people that are on the mailing list and paying attention. I think we've had an issue before, at least, where some people joined the meeting but weren't on the mailing list. So somebody was like, "Man, what happened to the meeting?" Like one of them got canceled for a conflict because I had something going on. A bunch of people showed up and they're like, "Where was the meeting?" I'm like, "Well, I sent something
Yeah, I
to the
guess it
list."
was you've been at a conference or something, right? You did a
Yeah,
presentation. I
yeah,
guess.
yeah. I think it was SIGCOM, right? Yeah. Yeah,
exactly.
I was trying to figure out, okay, how am I going to make this work? And then somebody asked me, "Oh, we need you to chair this session." I'm like, "All right, well, I guess it's not going to work."
No.
Anyway, all right,
Okay.
sounds good. I guess we'll see you next year then. Have a nice Christmas, New Year's, holidays, whatever's going on your end. All right,
Yeah, same to you. Thank you. And
sounds good.
well, I'll send out some stuff with respect to FOSDEM. So
Oh yeah, sure.
we're
be
still
good.
in contact until then, as the deadline is right in the middle of vacation, kind of.
Right. Well, I mean, if you guys want to meet, I guess the 27th is the day before the deadline, if you guys want to have a discussion or something, just over that talk, then, that works too. So.
Yeah.
Let me
Well,
know.
I guess we can figure this out next week, and from
Right.
previous submissions, that's not like scientific conference, so it's
Yeah.
much more easygoing. So I guess there won't be a big hassle. But yeah, we'll see. I don't know how much submissions they will get for this conference. I don't know.
Right.
We'll see. Okay, cool.
All right. Sounds good. Well, see you
Then,
guys.
I guess.
See you guys on the 10th then.
Yeah, have a good time.
All right. Will do.
Visit friends and family and everything, and then we're back online next year.
Sounds good. Sounds like a plan. All right.
Right.
Talk to you.
Have a good time. Bye.
Bye.